I've occasionally seen people on YouTube discuss which matters more if you're shooting a rifle downrange. Does it matter more if you have a crosswind uprange or a crosswind downrange? This problem is actually very complicated, but I'm going to make it look very easy using just some high school algebra and a slight touch of physics and calculus that I'll explain. So if all you have are high school algebra skills, at the end of this video, you'll know how to use a basic physics problem and some basic calculus. I've also done other videos showing the basics of calculus, and I try to make all of my videos or most of my videos so that somebody can understand them with just high school or middle school algebra skills. So you can see those videos if you want. Okay, so this is a tough problem. It was very difficult for me to figure this out. It took several months. This is one of my 3 hardest videos. Another video I did that was really hard was figuring out the velocity of water level rise in a bucket. And another video on the probability of 2 bullets colliding. So these are 3 problems that were so difficult that I did not think I could solve them. But eventually I did. I've done some other really complicated videos as well, but I was better equipped to solve those, meaning by the time I did those complicated videos, I had more math skills and I was just better off in understanding this. So this is like a really complicated jigsaw puzzle. The first 1 or 2 times you do it, you're going to be slow and you're going to have trouble explaining it. But after you've done it a few times, you should get really quick and be able to do the problem really quickly and be able to explain it really well. So I think that's where I am right now. So that's why I'm reshooting this video. All right, so that is the intro. On to the problem at hand. Here's a situation. We have a shooting range right here. Here's the shooter. And we're looking down on the course, so we have a bird's eye view. This is all grass right here that we're looking at. So say this way is north, straight ahead. To the right will be east. The shooter is shooting straight east or due east. We have a crosswind blowing due north, and that crosswind will either blow on the first 1/4 of the range, or blow across the first 1/4 of the range, or that crosswind will blow across the last 1/4 of the range. So the question is, if the bullet encounters that crosswind over the first 1/4 of the range, that bullet is traveling faster, so it will not be in that crosswind as long, and thus it's not going to be blown off course very far because that crosswind only blows across the first 1/4 of the range right there. However, that bullet will experience now a geometric multiplication of its deviation as it deviates off course. In other words, since it gets blown off course here, say a unit of 1 right there on the first 1/4 of that course, or 1/4 of that range, that means when it gets to halfway down, it'll now be off course 2. When it gets 3/4 of the way down, it'll be off course 3. And when it gets to the end of the range, it'll be blown off course a total of 4 units, or 4 times as far compared to its initial position uprange when it exited that crosswind. So what we're looking at here is a narrow angle carried out over a long distance. But now let's say that bullet travels downrange and encounters no crosswind until the last 1/4 of the range. The bullet will be traveling slower at this point because of drag as it goes through the air. And since it's traveling slower, it'll be in that crosswind for a longer time, which means it'll be blown off course farther. So this means you could draw a triangle from where the bullet entered the crosswind down to where it hit the target area at the end of the range, and this will make a triangle. So which matters more, a triangle with a wide angle carried out over a short distance, or does it matter more if that triangle has a narrow angle but it's carried out over a longer distance, which is what would happen if that bullet is blown off course uprange? But one thing to consider is that wind is always going to have gusts and eddies, and it's going to be blowing irregularly all around. So practically speaking, I don't know how much this matters. Theoretically, if you were shooting over a really long range, so that bullet has a long time to slow down, and possibly you had some wind meters downrange and wind meters uprange, so you knew exactly that wind velocity downrange and uprange, and you also knew that that wind velocity was not changing and it was maintaining a fairly constant velocity, at least for long enough that the bullet could get down to it, then this might matter. But otherwise, this might just all be a moot point and an interesting puzzle to solve. So either way, I'm solving it just because I think it's an interesting question. Okay, so now I've showed some numbers right here, but I'm going to get to this and show what each of these numbers means and how I got to that point. First, I'm going to show the calculus version, and it's actually quite easy. And I can say that now that I've figured it out and done this problem several times. But then I'm going to show the non-calculus version, which is still just about as easy. I'm showing the non-calculus version just as a second method to verify that what I was doing was correct. And the non-calculus version isn't quite as accurate, but it still gives a result that's similar to the calculus version. So at any rate, okay, so just basic physics formula here. 1/2 at squared equals distance. 1/2 times acceleration times time squared equals the distance that something travels. Since all we're doing is comparing the same bullet and the same crosswind, I'm going to go ahead and eliminate the 1/2, and we can just say acceleration equals 1. And again, that's because we're just comparing the same bullet and the same wind. And all we're trying to do is find out which bullet gets blown off farther, or gets blown farther off course. The bullet 1 that encounters the crosswind uprange, or bullet 2 which encounters the crosswind downrange. And again, they are identical bullets. That was actually the first hurdle in solving this, is because there's so many possible factors, because as the bullet travels through, you have the drag of the bullet, the front of the bullet. You also have the drag of the side of the bullet because the wind is hitting it from the side. You have the mass of the bullet. You have the force on the bullet from the wind. And there's just so many things to consider, but again, I'm going to make this super simple. Another key in simplifying this is with your acceleration in the y direction. Remember, it doesn't matter how fast the bullet is traveling in the x direction. You could have this bullet just floating up, say, in a space station, and you could have a fan blowing a wind on it, and this bullet's just sitting here in the wind, not moving in the x direction, but that wind hits the side of the bullet starts moving in the y direction. That's all we're looking at right here. So even though the bullet is moving in the x direction, we don't have to consider that distance. All we need to consider is for how long the bullet is sitting in that wind and gets pushed in the y direction, which is the same math as if it was just sitting still and somebody pointed a fan on it up in outer space. Okay, so anyways, we've eliminated the 1/2 and the acceleration. That means time squared equals distance 1 in the y direction. Let's say that bullet is in the crosswind uprange for a quarter of a second. That means it'll be blown off course, 0.0625, and that is distance 1 in the y direction, which is right there. We don't even have to know if this is centimeters, millimeters, or micrometers, or whatever, because all we're doing is comparing the distance of the two bullets, one that encounters the crosswind uprange and one that encounters the crosswind downrange. Now, since the bullet downrange is going to be in that crosswind for twice as long, let's say it's going half the speed, thus it'll be in the crosswind for twice as long. You just take 0.5 squared, that gives you 0.25. So that means the bullet downrange is going to be blown off course 0.25 units. The downrange crosswind is the easiest one to solve because we don't have to worry about the slope of a line or anything. We know that that bullet is in the crosswind for 0.5 seconds, so we know it gets blown off course 0.25 units, and it's that simple. For the bullet that encounters the crosswind uprange, we need to get the slope of this line right here, and then we can find out where that bullet's going to hit downrange using the slope of this line and just basic high school algebra. First, we're going to do a quick derivative to get this slope, because notice this forms a parabola. Anytime you're dealing with something squared, times squared, that's going to form a parabola. So we need to get the slope of this parabola right at the point when that bullet leaves the crosswind. That bullet entered the crosswind right when it exited the rifle barrel, and then it exits the crosswind right here at 1/4 of the range. Also, I almost forgot to mention two important things with this calculus method here. First off, this x-axis, I cannot use distance here, I have to use time. And the reason is to get the slope of this line right here, where that bullet is exiting the crosswind, that bullet is flying up and forming a parabola, I have to use time right here to get that slope. I can't use distance. And the reason I have to use time on the x-axis is because I have to take the derivative of time to get that slope. And that is because the amount of lateral deviation of the bullet from the crosswind, that deviation comes from the amount of time that that bullet is in the crosswind. It doesn't have anything to do with the X direction that that bullet is traveling. So in other words, I can't say this is 200 yards, 400, 600, and 800 yards. I actually have to turn the x-axis into time. And let's say that the distance of this range here is going to be 1 second for the bullets. So yeah, maybe the range is 800 meters or whatever, but that actually doesn't matter. All that matters is with the average velocity of the bullet, it'll be on this range for 1 second. And 0.25 of those seconds, it'll be right here in that crosswind uprange. So what we can do is pretend that that bullet is traveling along in the X direction at a constant velocity. In reality, it's constantly slowing because of drag. But all we need to know is that the bullet is in the crosswind for a quarter of a second on the first 1/4 of this range. And being in the crosswind for a quarter of a second will cause a certain amount of deviation laterally. So once that bullet leaves the crosswind right there at 1/4 of the range, it doesn't matter how fast that bullet travels to get to the end of the range right there. It could take the bullet 1 or 2 hours, or it could take 1 or 2 microseconds. All that matters is that that bullet was in the crosswind for a quarter of a second, so it's pushed off course according to this parabola right here, a certain amount. And then as soon as it leaves that parabola, it will continue on that same trajectory in a straight path until it gets to the end of the range. So the time will give us 2 pieces of information. First off, the time will tell us how far off course that bullet has been deviated from the crosswind. And then next up, we take the derivative of time to get the slope of that line right there as that bullet exits the crosswind. So the time gives us 2 pieces of information, the amount of deviation and the slope. And then the trajectory of that bullet is going to be deviated off course right here, and that deviation will be geometrically multiplied as it goes down range. So then we use the distance of the course to find out how much that bullet has been deviated off course after its trajectory has been geometrically multiplied. Or I guess I could say the bullet deviation has been geometrically magnified this amount by the time it gets to the end of the range. Now the math will work out and the calculus will work out. So now what we want is the slope of this line right here, because as soon as that bullet exits the crosswind, it's going to stay on that straight path until it gets to the end of the range. To get the slope of a line, you just take the derivative of your equation, which is t squared. That's just d dx of t squared. You just bring your exponent down, subtract 1 from the exponent. 2 minus 1 is 1, so you end up with t to the first. So total, you end up with 2t to the first power is your slope. And what that means is you could plug in any point along this x-axis right here for t, multiply it by 2, and that will give you the slope of that part of the parabola right there. We use 0.25 seconds because that is when the bullet exits the crosswind uprange right there. So 2 times 0.25, that's 2t. That means our slope is 0.5. And I should have written that right here probably. M for our slope. Now we use the basic algebra equation, y minus y1 over x minus x1 gives you the slope. And the y value here is what we want to find at the end of the range. So we take y minus y1. y1 equals 0.0625. Divide that by x minus x1. The bullet here is at 0.25 seconds when it exits the crosswind. It hits the end of the range at 1 second. So we take 1 minus 0.25 for our denominator, and that equals the slope of 0.5. Then we just go through the basic algebra here to solve for our y right there, and we end up with 0.44. So distance 1 in the y direction, that is the final distance, so d sub 1 sub y sub f equals 0.44. That means the bullet has blown off 0.44 units right there. And what we do is we can compare that 0.44 units from the bullet that encountered the crosswind uprange. We compare that number to the bullet that encountered the crosswind downrange, and that was 0.25 right here. So as you can see, even if that bullet is traveling extremely slow at half the velocity at the end of that range, a crosswind uprange matters much more, about twice as much. Also, I made that bullet travel extremely slow at the end of that range there. In reality, bullets are not going to be traveling that slow before they hit the target. I just picked this number here at half the speed, which means it'll spend twice as much time in the crosswind. I picked such a slow velocity because I wanted to give that downrange crosswind the benefit of the doubt to try to make it up to the same deviation as the uprange crosswind. From what I've read, even with the really long shots, the bullet always maintains over half of its velocity when it hits the target, because by the time it gets down to going half the velocity, it's such a far distance, you're going to have some pretty bad accuracy. All right, so that was the calculus version. You can actually see it's pretty easy. I spent a lot more time explaining how to set up the problems than actually doing the problems. To actually do this, as you can see, it's only like a page and a half, and I wrote really big here, so it's actually really simple to figure this out. All right, now for the non-calculus version, I can actually use a distance on the x-axis, so I'm going to do 2, 4, 6, 800 meters, and I'll show that on the next page. I'm going to compare the two graphs here. Notice in the first graph, when I used calculus, the bullet's going up into a parabola, but also notice this line right here that forms the slope of the bullet travel. It's not going to connect to the shooter. It's going to come down here and connect right here just in front of the shooter, right there, as you can see. So that's why this non-calculus version isn't going to be as accurate, and that's simply because the hypotenuse of our triangle doesn't actually match up with the shooter. And this is another thing that took me a really long time to figure out, because I totally did not think of using calculus to solve this problem. It's funny, in math classes, we learn how to do all the math, but sometimes the application of it can be a little tricky trying to figure that out. At any rate, okay, so here's the non-calculus version. The bullet's still going to get blown off course the same distance, 0.0625, because it will be in the crosswind for a quarter of a second. So to get our slope here, we simply take change in y over change in x, 0.0625 divided by 200 meters for the x-axis. We end up with a slope of 3.1 times 10 to the negative fourth. A couple of things that are important to note on this. Notice here we have a really small slope, but that's because we're actually using a distance on the x-axis in meters, and we're not using a time. And secondly, notice that the slope is going to be shallower here because the slope is going to connect from the shooter to downrange. And when I derive this slope from a parabola, you're going to end up with a steeper slope, because the farther you go down that parabola, the steeper your slope is going to get. So if you draw a slope on a parabola, you're going to end up with a steeper slope, so you're going to end up with a greater deviation downrange. Or I guess I should say you're going to have a greater total deviation by the time the bullet gets downrange, simply because your slope is going to be steeper because it came off of a parabola. Now we solve for our y. It's y minus y1 over x minus x1 equals slope. Now we know our slope, 3.1 times 10 to the negative fourth. Now we can solve for where the bullet will land downrange. If someone were to phrase this as a word problem on a high school algebra test, they would say, given the slope of 3.1 times 10 to the negative fourth, and a line that passes through 200, 0.0625, what will y equal when x equals 800? We just plug in our numbers here. Y minus y1 over x minus x1 equals your slope. 800 minus 200 equals 600. So you have 3.1 times 10 to the negative fourth times 600. And that will give you 0.1875. So you have y minus 0.625 equals that. Go ahead and solve for your y1 final. Or I guess a better way to say that is the final distance of bullet 1 in the y direction. And that's going to equal 0.25 right there. Oops, right here. It's going to equal 0.25 right here as the bullet travels in a straight line. And we already know from the previous problem that the final distance in the y direction of bullet 2 is 0.25 also. So here you can see that they actually have the same deviation, whether the bullet encounters the crosswind uprange or downrange. But again, this is with a bullet traveling at half the velocity downrange. So this bullet is traveling so extremely slow, it's not realistic in most situations. But only if the bullet is traveling that slow, it will have the same deviation as the bullet that encountered the crosswind uprange. So there you have it, uprange crosswind versus downrange crosswind. A lot of puzzle pieces to put together here and a lot of things to figure out, such as having to turn that x-axis from distance into a time to use the calculus version, and using high school algebra to get the slope of your line, and then also realizing that since you're dealing with the identical bullet, uprange and downrange, you don't have to worry about the bullet's mass or the drag on it, either the front of the bullet or the side of the bullet. So a lot of things to figure out in this puzzle, but hopefully I made it look at least fairly easy. Granted, this is a long video, but I think every step was actually really simple and just involved high school algebra. So that's it.